So what we're going to do today is a couple more examples of queues. The first one will be a long version where we do an MM3, where we get all the formulas, do everything that you need for the take-home, and then do another shorter version, a finite one, that is similar to one of the ones in the take-home. In terms of the take-home, I thought I didn't need it, but when I had PC Tech make a PDF, it was missing stuff. It says it's missing some of the characters. I'm not sure how that works. So I have now downloaded PDF, Adobe, and hopefully when I try again, it'll put everything in. So after class, I'll try to redo the PDF and re-upload it. And hopefully this time it'll look nicer. But a couple things with it. So pretty much the missing things the character doesn't like. It doesn't like FI for some reason. So for example, I ask you in a few places to find something, and you just see kind of a box with ND. So if you see that, it's find. And then it doesn't like lambda. So there are a couple boxes, and the places where it's missing there are lambdas. But at the end of class, we'll end a little bit early so you can ask me what specific things are. I've set up groups on Blackboard. I haven't done this before, so I'm not sure exactly if I'm going to have to do anything else. I've made them completely open. So right now I have 10, and you should be able to see the groups. You should be able to, when you click on them, you should be able to see who's in the groups, and then you can sign yourself in. Once you're in, you should be able to set up discussion boards. You should be able to do this, the Collaborate Ultra, where one of you can lead, or you can have a few of you, so you can do this whiteboard type thing. And there should be other things. So pretty much all the tools I think that Blackboard has, I allowed. So you'll just let me know if there are problems. Also, one of the days next week, now I'm leaning to Wednesday, I'm just going to do an office hour type thing where I'm going to just have you come in, work on it. I think I will try Zoom instead, because Zoom lets you do more group things, so I can split you up into groups, the ones that you're already in, and then you can talk to each other and I can talk to you and so on. But I'll decide that later. So probably Wednesday, but it'll depend on how quickly things go. Okay, so today, and quick little thing is that tentatively the take home is due a week from Monday, which is the 30th. We'll see how things go next week. So some of the problems should be pretty easy. So let me look at from the packet, one of the problems, which in mine is on page 26, but I think on others is on page 28. And it is problem 8. So I'll write down everything so you have it. So we have MM3. Where you have a server of some sort, 15 jobs are arriving. That's supposed to be the word arrive. Arrive per hour. And it takes 12 minutes to finish. Again, sorry about the writing. What it does, if I write too quickly, it kind of puts things together. So I was going to complete it from yesterday's, but then I just made up one, so I don't have the numbers here. So let me just start from the beginning. And then if you want, we can go back and get the EVA and Q for that. So this way, we start again, do everything, do another one where we get the steady state probabilities and so on. So here's the setup. And so A is what we did yesterday. Let's find the steady state probabilities. for this page, let me just get lambda and mu, and then erase and go to the next one so I can try to put most of it on one page. So here, lambda is as given, and mu we just have to get in terms of per hour. So we're getting 14 jobs arriving per hour, so that's lambda, and it takes 12 minutes per job to finish. Therefore, what is mu? So 5, it's 12 minutes for each, and it's 5 minutes per hour. So as I said, let me now go to a new one and try to fit all of this part A on it. So any questions before I move on? Okay. So again, these numbers are the number in the system or store or whatever you want to think of it as. And the arrival rate is a constant 14, so it's always moving up at a rate of 14. Remember, that means things are going quickly, not that we can jump. In some ways, we'll find out. We probably don't need that many. I just want to start getting the pattern. And so we found that this was 5. What would be the second number? So continuing off what we did yesterday. Because if it's 5 per server, then here now there are 2 people, so 2 servers are working, so it's double. And this one will be this one, 15, because now we have 3 servers working. And now from now on, it's going to be again the 15. Oh, so because once we get here, so if I'm here, this is saying there are 3 people in the store. There are 3 servers, which means each of the servers is now working and no one's waiting. This is saying now there are 4 people in the store. There's still only 3 servers, so 3 servers are still only working, and each of them can serve 5 people per hour. So there are now 4 people, only 3 servers are working, and that'll be true from now on because there are a maximum of 3. So is it not 14? Because 14, remember, in some ways these are independent. The 14 is the rate at which we're arriving, which is not the number of arrivals. So we get that. So we get our same as yesterday, where we our relationship, and remember we're kind of reading backwards. P1 is equal to this ratio times P0. So therefore, what is P2 in terms of P1? Again, reading to the left. So what's the number? What's the fraction in front of P1? No. All right, so 14 over 10. And I could multiply it out, but I want to see the pattern, so I'm going to leave it as 14 over 5 times 14 over 10 P0. And then P3 is what times? So 14 over 15. And again, I'll not multiply it out. And one more, and you'll see this is really as far as we have to go. So P4. So P4, the fraction is, again, the 14 over 15. And you can see now I'm just going to keep multiplying by extra 14/15 because now the ratio is constant. So I do the 1 is equal to the sum of all of them. I can factor out the P0, and looking at the numbers above, I have the 1 for P0, the 14/5, the 14/5 times 14/10, 14/5 times 14/10 times 14/15, and plus da da da. And as I said yesterday, in some ways we could get this as a formula, but I find it easier just to notice that eventually it's geometric. So for example, at this point through here, it certainly is not geometric. To go from the first to the second, I multiply by 14/5. To go from the second to the third, I multiply by 14/10. But where does it start being geometric? Which term? And there are two ways of answering this. So the third one, so if I can start with this third one here if I want, because from the third term to the fourth term, I multiply by 14/15. From the third to the fourth, I multiply by 14/15. So from there on, so starting here, this part is geometric. And depending on how you do geometric, you can either factor out the 14 squared over 5 times 10 to make the first term 1, or you can just assume that's a, which is the first term, and then use the fact that then r is 14/15. And when I do that, I get nothing very nice. But I'll leave it as a fraction. Rewrite it. I get, when I add the 1 and the 14/5, I get it's 313/5 times P0. So therefore, P0 is equal to 5/313. P1 is 14/313. I should stop doing fractions, as you can see. And I guess I did from there on. And da, da, da. And from then on, to get from one to the next, so that P4 would be this number, the 0.058 times 14/15. And then I keep multiplying by 14/15. So this we did yesterday. So here's a second example. Any questions on this? As you're thinking, let me just note that when we get to part B, where we're getting E of n, or E of nq in particular, really, it'll turn out that we need through P3. So if we're doing MMC, we need through PC to be able to get the E of nq, which is why I stopped at P3. So any questions on all this? So we're going to be using the probabilities here. So give you a minute to write them down if you want to have them in front of you. And then I'll erase. Okay, so let me erase. As I said yesterday, it'll turn out to be easier to do E of nq because if we're looking at the number of people waiting in line, that's when it starts being geometric. So it makes it slightly simpler. It makes the formula a little bit nicer. And so this is where we stopped yesterday. So let me just give you, here is the formula. As I said, we could get it as we did with the MM1, but this time I'm just going to give it to you. And my rows and p's look similar. So in the numerator, it's rho over c. And remember that rho is equal to the lambda over mu. And in the denominator, it's 1 minus rho over c squared. And then pc, so that's the probability of c. So here, since it's mm3, c is equal to 3. And therefore, we get that this is which in some ways you might expect, the 14 over 15, which comes from, that's the ratio for the geometric. And then 1 minus that same thing, squared. And then P3, which was in the last one, was the 0.058 dot, 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 dot. As usual, you should be checking by numbers. For this one, I get that this is, however far you want to go, at the 12, so 12.2735. Okay. So now, from here, we can get E of W. So we'll now rotate around to get everything else. So this is probably part C, but we know that from Little's theorem that the relationship between W and NQ, both in terms of lines, is E of W is equal to 1 over lambda E of NQ. In this case, the arrival rate is the constant 14, so we don't have to worry about getting the average arrival rate. It's just 14. So I can divide that by 14. I get that. As I said, you should be checking these numbers. And then once I have E of W, I can get E of T. Because I know that the T, which is the total time in the system, is equal to W, the time I'm waiting in line, plus S, the time it takes to be served. And the time it takes to be served is purely exponential, and the expected value of an exponential is just 1 over a parameter, which is mu. So here, this is the 0.87668. And even though it eventually gets multiplied, the mu is always just the original mu, because this is looking at service time. And when I'm actually being served, I don't care how many people are being served. I don't care how many servers there are. If there are 10 servers, it doesn't help me because I'm being served just by the one person. So I get a number. Just adding 0.2. And now I can use that to get E of n. It's supposed to be an n, which I know is, again, by Little's theorem, lambda times E of t. This time I'll be lazy, just the 15.07. So here's the formula we need. And that's telling us if we want to get all these things for MMC, we need to get the steady state plays out through PC. So MM2, we just need P of 2. MM3, we need P of 3, and so on. So if we continue the one from yesterday, we wouldn't have to do quite as much because we would only need P of 2. Okay. So any questions on this one? This is now new. But you can see the only new thing is this new formula, and everything else loops around. So any questions on this? Okay, so let me erase. And let me introduce another formula that in theory we could get. And I'm not sure why I give this one as a CDF instead of a PDF, but why not? So similar to MM1, we could look at the probability, find the density function for the sum where we did the conditional density functions depending on how many people are there when we arrive, multiply by the probability of that and add them all up. Given the last one, it should be sort of intuitive that, again, we're not going to get t because it'll start being a geometric type thing once we start having a line. So instead, we'll get the density function for w, not the function for t. So we'll get the density function, or in this case, the CDF, for the time we wait in line, not for the total time we're in the system like we did for MM1. So here's the formula. Now the actual question is, find the probability that the time I wait in line is less than 1, in this case, hours. And this is for a person arriving, which you'll see is important in a second. So you'll see that this is sort of a mini tree type thing, because there are two cases. We have MM3, so if I get there and there's no one in line, well, I don't wait in line at all. No one in the store, I don't wait in line at all. If I get there, there's one person in the store, I don't wait at all. So there is a non-zero probability that I don't wait in line at all. And then the other case is I get there and I will have to wait in line. And then the question is, what's the probability I wait in line less than 1 hour, given that I have to wait in line at all? So first, before I get either of these two, so the second part will be using the CDF I just introduced. But let me first ask, what is the probability that the time I wait in line is equal to 0? Sorry. And so when we start it, and you're just going to tell me what the last one that's included, which is obviously if I get there and there's no one in the store, I don't wait. Obviously, if I get there and there's one person there, I don't have to wait. So how far do I go? Do I go through P2, through P3? How far do I go? It's the last term I'm going to have. Yes. This is as far as I go. And that's why I put this in, because if I get there and there are 3 people there, there is no line, but I'm going to have to form a line. So I forget if I got this number or not. I think I did not, because I think I messed it up. but let me leave it like that for a second. And the other thing we need is what is this CDF, but this particular one. So as with the last one, C is equal to 3, mu is equal to 5, rho is equal to, actually, let me just do the whole thing. Rho over C is equal to 14 over 15. Rho is, again, the lambda over mu, so the 14 over 5. C is 3, so 14 over 15. So if I plug that into the formula up here, I get, forget what it comes out to, so 15 times 1 minus 14 over 15. So just 3. Wait, no, just 1. So just this. So let me leave it there because you're going to double check me as usual. Is that okay? Is that what I get? So let me actually get this. So you have access to the one on the other page. Let's get what that number is. So let's make this specific. So I get 0.1233. For some reason, I don't have it in my notes. Actually, I know why I don't have notes, which I messed up the calculation and I just crossed off. So does someone get that? If not, if you don't have the calculator in front of you, I'll just assume it's correct for now and you'll double check the number. Okay. So let's put it all together. Except you just lost the, notice the C in front of the mu. So it's not 5, it's 15 times the 14 over 15. Oh, sorry. So let's put it all together. So the probability that W is less than 1 is equal to this, assuming this number is right, is equal to the probability of 0 plus the probability it's more than 0, which is 1 minus the 0.1233. And now, here, let me go back. I want to find what is this probability. And so how do I use a CDF? So how do I what am I going to plug into the CDF to get that? Or what do I have to do to get that? Somebody's only asked this one here. So this we've used a few times. What is the definition of a CDF? It's the probability that x is less than or equal to x. So since I want to find the probability that W is less than 1, I'm just going to plug in 1. So therefore, this will be that. Oh, the thing above that first digit is it was a stray mark from when I was pressing down with my finger before. So that should just be 1 minus 0.1233. So it's not a T. That top of it's just a stray mark. Sorry about that. And again, might as well try getting a number. get something like that. All these numbers you should double check. So this is part of one of the things that's on the take-home. Questions about this? So D in the thing I'm going to leave off. So let me erase this. And I'm going to do E, another question on the take-home. And this type of one, I wouldn't ask on an in-class one. So what we want to do is find what is the probability that T is less than 1, where T is now the total time. And first, let's break it up and then see what we need. So the first thing is similar to the last problem. There are two things that happen. And let me put over here just so I have the two variables again. I want to remind you that the total time in the store will be equal to W, the time I wait in line, plus S, the time it takes to be served. So the two cases are, I could get there, I don't have to wait in line, in which case the probability that T is less than 1 is just strictly the probability that S is less than 1 times the probability that W is 0 and then plus the probability I do have to wait in line times the probability that S plus T is less than 1. S plus W, sorry. So here are the two cases. I either get there, I don't have to wait in line, but I do have to be served. So the time I'm in the store altogether is just the time it takes to be served. Or I get there, I'm going to have to wait in line, and I'm then going to wait in line and have to be served. So what we're going to need is two things. So the probability that W is 0 is the same as the last problem, which I forgot to write down. I think it's like 0.1. Is that the one oh, actually right there in the chat. So that is the probability that W is 0. But what we need for the others is this and this are continuous. So I'm going to need density functions, one of which is easy. S is the time it takes to be served, and we are assuming that's exponential. Therefore, it's just the exponential that we're given with the given parameter. And again, this part is strictly, oh, actually it wasn't 4. What was the, mu was 5? Is that what it was? Wasn't 4. Not sure where I got 4 from. Was mu 5? I think so. Yes. Okay. So that part of it is the one variable. And for this, S plus W is T, so what I need is T. Interesting. So that is two variables. We assume S and W are independent. So going back to 3081, we know that if something is independent, that the joint distribution is the product of. So the exponential we just got, And then FW, we just have to go back. We had, so officially I'm being lazy. It's FW of W given W is more than 0. So we found the CF was, and I'm going to make it a W. I think I used T in the last one, but we have a different T here. So that's what we got before. How do I get the PDF given the CDF? We haven't done it for a little while, but yeah, derivative. So this is going to be just when I take the derivative, it's going to be that. Okay. So now we need the two integrals. So we want to find the probability. One of them is easy. So I'm going to be able to put that in. So the probability that S is less than 1 is just a one variable thing, so it's just a one integral. And that's pretty easy. And if I put in 1, I get negative e to the negative 5. If I put in 0, I get negative 1. So I'll just flip it so I get that probability. I'm going to try to make things small so I can fit this also here. So if I want to find the probability that the sum is less than 1 of S and W, well, that's now two variables. So do the usual double integral thing, which is I draw it. And it doesn't really matter which is which, I guess, W and S. So this is going to be a double integral of our joint PDF. Not sure why I'm doing that order, but why not? So what are the limits? So the limits, so first let me get this point, which we're going to be using in a second. So when S is 0, W is 1, so that's 0.10. So what are the inside limits? Here's our region. The lower limit is obviously the 0. And the upper limit is the function. So S is equal to 1 minus W. And I can see from my picture that W is going from 0 to 1. And I'll start this, but I don't think I have room to finish it. You'll see the first step, it's not too bad, although it is a little tedious. So to get this, so I take the antiderivative with respect to S. The e to negative W is just going to stay there. The antiderivative of 5 e to negative 5s with respect to S is what I have up here. So I'm going to get that. If I plug in S equals 1 minus W, I get that. If I put in S equals 0, I get 1 times e to negative W. I get that. So if you look at this, looks worse than it is because that first term, I can put it together. It is, I have a negative 5 plus 5W minus W. So this term becomes minus e to the minus 5 plus 4W. That's supposed to be a W. And we take the antiderivative, which isn't too bad, and so on. And we keep going. Once we get that, we have the 1. This would give us something, and we get into here. using the fact that that is probability that W is equal to 0, which means the probability W is more than 0 is equal to 1 minus that. So in some ways, you can see why this would not be something I'd have you do in class, because it's not necessarily difficult, but very tedious and fairly lengthy. So this you're going to try on the take-home. So questions on the steps here. Okay. In some ways, the usual thing, which is this stuff is also written up in the notes that I now have online. For W, so the CDF for W we got from the previous part, so part C, which was that new formula I gave you, 1 minus e to the negative c times mu times 1 minus rho over c. So this part right here, we got in part C. And then we took the derivative to get the PDF. So that the reason we didn't show any work is we already did the work. Okay. Okay, so that's one of the problems. Let me do one more, shorter, type that could actually be on a test. Let's see how far we get with it. So let me erase. So let me ask once more. Any questions on this before I erase? So this is, in mine, is the last problem in the second part, which on mine is page 23, but in the other version it might be 25. And so this one, like, I forget which problem it was on the take-home, but we have So we have a food truck. This is the arrival rate, which is the new part, because now notice the arrival rate is not constant like it usually is, because remember arrival rate is lambda. And we have one server and this is per minute. Oops, it's supposed to say per minute there. So the arrival rate is this number per minute, where n is the number of people in line. If there's one server who can serve one person every 2 minutes. And so the usual first question, find the steady state probabilities. So first, before I go to the next page, so I'm going to put this on the next page, but let's start putting the numbers, which I'm going to put on the graph next one. So if the total number of people in the store is 0, then the number of people in line is 0, and plugging that in gives us 2. If the total number of people in the store is 1, what is n? How many people are in line if there's one person? So not one, because if there's one person in the store, how many people are waiting? And that would still be 0, right? Because the one person is being served. And so therefore lambda is still 2. And I think I'm going to make this shorter because this is going to be a long problem. So if you don't mind, I'm going to switch this to just 0, 1, and 2. So if the total number in the store is 2, now what is n? And now it is 1. And so if I plug that in, I get lambda is equal to 1. If total is 3, then n is equal to, what am I up to, is 2. And goes to lambda is equal to 2/3. So in the original problem, I would do one more, but to keep it short, let's make it that, because there isn't much time. So actually, let me write that down so I have them for the next one. So any questions on these numbers? Because I'm going to go to the next page to do the things. Oh, so here, there's one server. So there's, for all of these, there's always one line, but there's one server. So I think at the very beginning, I talked about having more than one line, but we always assume there's one big line, and then they're split into the different servers. So any other questions on this? So when will n drop? I'm not sure what you mean. So in this setup problem, you'll tell me this is what you mean. I'm saying that the arrival rate is given by this formula if n is equal to 0, 1, or 2, and if it's anything bigger than 2, the arrival rate is 0, which means the total number of people that can be in the store is 3. So I'm not sure what you mean when will n drop as total increases. So as the total number of people in the store increases, the total number of people waiting in line also increases. It's just that at some point it stops because no one else is allowed in the store. Is that okay? And I said, I'm not sure what you're asking. We do have. So this is as far as we go. So as the total increases, it will always increase. And here, this is as big as it can possibly be, given my setup at the top there. Okay. So any other questions on this? Okay. So let's build the thing. So we have we found that the total can be at most 3, so that's as far as we need to go. We found that this is 2. We found this is 2. Actually missing 1. We found this was 1. And we found this is 2/3. So we found that the arrival rate becomes 0 after 3, but that means we will go to 4, which is why I went to drop off 1. And we had, they can serve one person every 2 minutes. So therefore, mu is equal to, again, if I put it into minutes, is 1/2. So half a person per minute. Okay. So we get the steady state probabilities. So again, we have done many times now, the ratio, so 2 over 1/2. Oops, sorry. So you can see why I went to stop, because it goes pretty far. So first, for any questions on the setup, so the graph at the top, and then we do our usual thing. 1 is equal to the sum of the probabilities. I'll pull out factor out P0. So I get those. Since we don't have too much time left, I'm going to skip part of it, which is get even Q. Actually, let's get one of them. Let's get even Q, because then I'll use it. Do the shorter one. Also, this is the more confusing one. So even Q, remember, is we're going to multiply the number of people in line times the probability. So obviously, if there's no one in this, there's no one in line. If there's one person in the store, how many people are in line? Yep, 0. And then from there, it now keeps going up. So 1 times P2 plus 2 times P3 plus 3 times P4. So we get that number. And then if we want to get E of W, we need lambda A. Because here you can see the arrival rate isn't constant, so we have to get the average arrival rate. And again, remember, we're reading forward. So at 0, the arrival rate is 2. At 1, the arrival rate is again 2. And then at 2, it is 1. And at 3, it is 2/3. And at 4, it's 0. So that just falls off. So let me try quickly getting these numbers. those two numbers. And then I know that, for example, E of W is equal to 1 over lambda A E of NQ. Remember, when I'm going from either W to NQ or T to N, I need to use this average rate of arrival. So any questions on this? Okay, so as I said, I want to end a little bit early, so if you have quick questions about take home, I'm assuming you haven't really looked at it yet, but just in case. But let me remind you that the groups are open now. You're going to let me know if there are problems. And probably tomorrow I'll send an email saying which day we're just going to meet to talk about and work on the take home. As I said, probably Wednesday, but I'll send out an announcement. So any questions on this? Okay. So it will depend. So how many of the probabilities do we have to calculate if it's in? So for example, we just did MM3. We found in the formula we need P3, which means that's as far as you would have to go. So in general, for MMC, you need to go through P of C. MM1, usually I'd still have you get at least a couple of them, so 0, 1, and 2 maybe. But other higher ones, MM2, we just need to go through P2. MM5, you would have to go through P5. I'm not going to make you go that far, but we'd have to go there. In some ways, we could go further than that, but if you look at the formula, again, the formula to get E of NQ only needs P of C. So we certainly could use ones after P of C, but we don't need them. And also, if you look at the last problem, when we were getting the probability of how long we have to wait in line, we actually didn't even need P of C. We needed the one before it. So we just, for MM3, we just needed through P2. So to find the probability that we wait in line, we just need one less than C. And to get the expected number in line, or number in waiting, we just need C. So we can go further in C, but we don't need it for any of our formulas. Any other questions? Okay. So asking about pass-fail, what I've heard, and actually I heard, you should have gotten the same email. Let me actually just go back and forth here. Let me look at my email. Never mind, it's not letting me go in. But yeah, I got one, I think indirectly from the university where they said students are now allowed to take up to 2 classes pass-fail. So if you want, you could take 2 classes pass-fail. You'll just have to let the person know. I forget if I got that directly or not, but you should be getting an email about pass-fail in general. Oh, interesting. So usually the students get stuff before I do, but okay. Oh, so asked about E of NQ. So remember, the formula we did in the last problem isn't a general formula for E of NQ. It's only the formula if we're looking at MMC, which assumes that we have first, a constant entry rate, and second, it is infinite. So MM2, MM3, MM4, stuff like that. Because remember, we had another formula for MM1. So MM1 had a different formula. So we'll have formulas for MM1, for MMC, and then finite ones we're just going to do directly. Right. So it's constant entry rate infinite, but you don't want to use it for MM1 because we have a simpler formula in that case. It still works, but it's kind of silly because we have simple formulas. Anything else? Oh, okay. E of n, so in some ways it's not the E part of it, it's the N in NQ. So N is the total, let's pretend we're doing a store. So N is the total number of people in the store. NQ, the Q for Q, is the number of people waiting in line. So in general, if I have 2 servers and there are 5 people in the store, then N would be 5, and NQ would be 3, because of the 5 people, 2 are being served and 3 people are waiting in line. Is that okay? Okay. So let me stop recording. I'll stick around for a few minutes, so if you have any quick questions, but otherwise we're done. And what you should be doing for the weekend is starting looking through the take-home. And you're going to email me if problems come up. As I said, I'm going to try to redo the PDF, so hopefully it'll look nicer. Otherwise, have a good weekend.